Welcome to this session on index selection and design. Here you'll learn how to choose the best indexes to boost your database query performance. The focus will be on optimizing your databases for faster and more efficient data retrieval. Let's begin by understanding what database indexes are. At a fundamental level, database indexes are data structures that enhance the speed of data retrieval operations on database tables. They are similar to the index in a book, which allows you to quickly locate specific information without having to read the entire book. These indexes are organized in a way that supports efficient data retrieval. Importantly, indexes are separate from the actual data tables. This means they don't alter the content of your data, but rather provide a faster way to access it. Some of the benefits of using database indexes are faster query execution, reduced input-output operations, improved sorting performance, and efficient data access patterns. Now let's explore some common types of indexes used in databases. First, we have B-tree indexes, which are the most common type. They organize data in a balanced tree structure, which makes searching, inserting, and deleting data efficient. B-tree indexes are great for both equality and range queries, and are the default index type in most relational database management systems. Next are hash indexes, which use hash functions to map keys to values. They are extremely fast for finding exact matches, but are not suitable for range queries or sorting. Hash indexes are best for equality comparisons, especially in in-memory databases. Bitmap indexes use bit arrays, also known as bitmaps, for each possible value in a column. They are very efficient for columns with low cardinality, meaning columns with only a few distinct values. Bitmap indexes are particularly useful in data warehousing and for analytical queries. Lastly, full-text indexes are specialized for text search operations. They enable you to efficiently search text content, offering features like stemming, ranking, and relevance scoring. These are commonly used for document search and text analysis. Let's discuss the criteria for selecting indexes in a database. When choosing the right indexes, there are several key considerations to keep in mind. First, examine your query patterns and how frequently they occur. Knowing which queries are run most often will help you optimize them effectively. Next, consider column selectivity, also known as cardinality, which refers to the uniqueness of the values in a column. Also, the distribution of data within your columns can affect index performance. Additionally, keep in mind how often data is updated, inserted, or deleted, as these operations can impact index maintenance. Finally, storage constraints such as how much space you can allot for indexes is a factor. Let's look at an example of query analysis. Imagine a common query that selects data from a customer's table where the last name is Smith and the status is active. To optimize this query, you could create an index on both the last name and status columns. Here's the structured query language code to create such an index. Create index name on customer's table with last name and status columns. Here's how column selectivity affects index effectiveness. Let's start with low selectivity. This refers to columns with few unique values, such as a gender column with options like male, female, or other. Indexing columns with low selectivity is generally less effective because the index would return many rows for each value. Next, medium selectivity columns have a moderate number of unique values. An example is a state column in a United States address, which has 50 possible values. Indexes on these columns can be moderately effective and are often useful when combined with other indexes. Lastly, high selectivity columns have many unique values, such as an email address column where each user has a unique email. Indexes on these columns are very effective because they help quickly narrow down to a small number of rows. As we move from left to right in this diagram, the index effectiveness improves. Composite indexes are indexes created on multiple columns in a table. There are several key principles to remember when using them. A primary principle is that the order of columns in a composite index matters. It's best to put the most selective column first. These types of indexes are particularly useful for queries that involve multiple conditions. Also, a single composite index can often replace the need for multiple single-column indexes, simplifying your database design. For example, consider creating a composite index on an employee's table with the last name and first name columns. The SQL code might look like this. Create index name on employees with last name and first name columns. This index would be effective for queries that search based on last name, or those that search based on both last name and first name. Indexes provide various benefits and drawbacks that need to be carefully considered. Here's a look at some index trade-offs. Query performance. The benefit is faster data retrieval, the drawback is slower write operations. Storage space. Smaller than tables but requires additional disk space. Maintenance. Indexes such as B-trees are self-balancing, but requires monitoring and tuning. Write operations. No impact on select queries but slows insert, update, delete queries. Query optimizer. Better execution plans, but can be ignored if poorly designed. Let's explore how to monitor and maintain indexes to ensure optimal performance. Here are some monitoring strategies to consider. First, you should track index usage statistics to see how often each index is being used. Next, it is essential to identify unused indexes that are taking up space but not contributing to query performance. Index fragmentation should be monitored, as fragmentation can slow down index performance. You can also analyze query execution plans to understand how the database is using indexes. Lastly, you should set up a regular maintenance schedule to keep your indexes in good condition. Here are some maintenance commands. To find unused indexes in Postgres structured query language, you can use the following query. Select index rel reg class as index underscore name, idx underscore scan as times underscore used from pg underscore stat underscore user underscore indexes where idx underscore scan equals 0. To rebuild a fragmented index, the command is reindex index name. Here are some index design best practices. First, index high selectivity columns. Prioritize columns with high cardinality, meaning many unique values, for better query performance. Also, consider query patterns. Create indexes based on actual query patterns and frequently used where clauses. When using composite indexes, place the most selective columns first for better performance. Another practice is to avoid over-indexing. Too many indexes can slow down write operations, so it is best to remove unused or redundant indexes. Consider covering indexes by including all columns needed by a query in the index to enable index-only scans. Lastly, schedule regular index maintenance to rebuild fragmented indexes and improve performance. Here's a summary of what we've covered and some next steps to consider. Indexes dramatically improve query performance, but come with storage and write operation costs. Choose high selectivity columns and analyze actual query patterns. Composite indexes should order columns from most to least selective. Regular monitoring and maintenance are essential for optimal performance. To continue your learning, we recommend exploring query optimization techniques, database partitioning strategies, and advanced indexing methods for specific database systems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.